Okay, so this is on Laplace transforms. So yesterday we looked at the relationship between Laplace transform of a derivative and the Laplace transform of t times f of t. So what does the Laplace transform do? It converts differentiation into multiplication by s and multiplication by t into a differentiation with respect to s, right, and it takes into account the initial conditions. So it's particularly well suited for the study of initial value problems for ODEs and PDEs. So we saw one example of an initial value problem for ODEs, correct, and then what else we saw? We looked at the Riemann-Lebesgue lemma, correct. Yeah, you have to assume that the initial value is C and then you have to carry on. If the initial value is not given to you, then you have to assume that y of 0 is a1, y prime of 0 is a2, y double prime of 0 is a3, etc. And then there will be this a1, a2, a3 floating around in your general solution, correct. All right. So now let us go one step further. Let us now start with an example. E to the power minus s is not the Laplace transform of any function f t of exponential type. Why is this? Suppose if e to the power minus s is the Laplace transform of little f, then what is the Laplace transform of t f t? It is minus f prime of s, which is e to the power minus s again. So take the difference, what do you get? Laplace transform of f minus tf is 0. Am I correct? Is it correct? Which basically means that ft into 1 minus t must be 0, but the uniqueness theorem, no? Laplace transform of 0 is also 0. So the two things must agree almost everywhere. That means that ft into 1 minus t must be 0 almost everywhere, and so ft must be 0 almost everywhere. But if ft is 0 almost everywhere, Laplace transform of f will be 0. It is not going to be e to the power minus s. So we get a contradiction. So although e to the power minus s goes to 0 as s tends to infinity, it is not the Laplace transform of any function. So just the Riemann-Lebesgue lemma is a necessary condition, gives you a necessary condition for a function to be a Laplace transform. It is by no means sufficient. In fact, generally a periodic function cannot be the Laplace transform of anything. When I say periodic function, I mean periodic in the complex domain. So e to the power minus s is a periodic function. It has an imaginary period. E to the power z is a periodic function with period 2 pi I, right. So e to the power minus s is also a periodic function. The periods are imaginary. So when I say that a periodic function cannot be the Laplace transform, the period could be real or imaginary, okay. Is that clear? So that's a interesting example, and a few exercises for you. I have not given any exercises as of yesterday, so here is a short list of 4 problems. Please write them pretty rapidly because we have to hurry up. I am planning to close the Laplace transform chapter today, but I do not know whether I will succeed in doing it, otherwise it will spill over for tomorrow. Find a function whose Laplace transform is ln of s squared plus 4s plus 5 upon s squared plus 2s plus 5. So capital F of s is given to be ln of s squared plus 4s plus 5 upon s squared plus 2s plus 5. F prime s becomes a rational function. When you differentiate the logarithm of this, you get a rational function. So you can find a function little f such that Laplacian of little f is this rational function. Now use those rules. If Laplace of f is capital F, Laplace of Tf is minus f prime. So essentially you would have recovered Tf, now you have to recover f, correct. So, once again what is the procedure? The capital F is this, capital F is this, you have to calculate capital F prime of S, correct. Please do this exercise. The second exercise is Bessel's function of order 0. Bessel's function of order 0, the value of the function is given at the origin, the value of the Laplace transform is given at 1. Find the Laplace transform. This is an example of a variable coefficient differential equation to which we apply the Laplace transform. The book of Schiff which you have will give you more examples of this phenomenon, alright. The Schiff's book will give you more such examples. The third exercise is pretty straightforward, but it is interesting. The Laplace transform of 1 minus e to the power minus t raised to the power nu is a beta function. And so I am taking my nu to be minus 1/3 and I am asking for the value of the Laplace transform at 1/3. Alright. And the fourth problem is compute the Laplace transform of 2 over t 1 minus cosine omega t. Remember we have calculated the Laplace transform of sin t by t, remember yesterday? Same idea has to be employed. Please do these exercises. Yeah. The last one is particularly interesting because it will give you an evaluation of the Frullani integrals. Right. All right, let us proceed further. So, last time I told you that we are going to compute some interesting integrals. What integrals have we computed so far? We have calculated the Fourier transform of e to the power minus ax squared, right, via ODEs. We found an ODE for the Fourier transform and we solved the first order ODE. The other example that we were discussing in the tutorial class was to attempt at finding the Fourier transform of 1 over 1 plus x squared. There were some difficulties when you apply the same technique, but I also told you how to circumvent those difficulties, right. But now the very efficient procedure I am going to give you of directly using the Laplace transform method. So, using Laplace transforms to calculate integrals. So, calculate the integral 0 to infinity cos omega x upon x squared plus a squared dx. That is, I want to calculate the Fourier transform of 1 over x squared plus a squared. Okay, you denote the integral by cos tx upon x squared plus a squared. Instead of omega, I am putting t and calling the integral it. So, what is the Laplace transform of I? Take the Laplace of this integral, take the Laplace operator inside the integration. Take the Laplace operator inside the integration. It is simply equivalent to switching the order of two integrals. It is just equivalent to switching the order of integration signs, that is all. And then Laplace of cosine tx is what? S upon s squared plus x squared, s upon s squared plus x squared. Now, you see that now you are integrating a algebraic function, a rational function in fact, which is immediate by partial fractions. It is at once computable by partial fractions. You calculate the integral and you get the integral as pi by 2a into pi by 2a s plus a. That is the value of the integral. So, we have computed the Laplace transform of I. Now, you need the original I. So, tell me the I whose Laplace transform is this? Pi by 2a into e to the power, pi by 2a into e to the power minus at, pi by 2a into e to the power minus at. So, the integral I of t equal to pi by 2a into e to the power minus at. So, that gives you the value of the integral I of t equal to pi by 2a into e to the power minus at. So, cos of x psi upon x squared plus a squared dx is pi by 2a e to the power minus a psi. Note that we have calculated the Fourier transform of 1 over x squared plus a squared. Here are some exercises for you, please write them down. The last one is quite amusing. You please do it, you are going to have a lot of fun doing it. And I am not going to do it in the tutorials unless you have given it a serious thought. Yes. And the answer is also quite interesting. And when a equal to 2 in the third, in the second one, what do you get? Integral 0 to infinity sine of tx squared, correct. Suppose a is 2 and t equal to 1, what do you get? That is the Fresnel integral. When a is 2 and t equal to 1 in the second exercise, the integral is a Fresnel integral, appears in the theory of Fresnel diffractions, correct. So, some of the well known integrals are computable via Laplace transforms, correct. Yeah, please hurry up with your writing, just write the integrals. All right. Here are some more, there is some more amusement for you. Yeah, I think computing integrals is quite fun, isn't it? It's always very teasing. What happened? Not clear? Cos x psi upon 1 plus x to the power 4. The Fourier transform of 1 over 1 plus x to the power 4. That is what we are trying to compute. All right. The last two are quite routine. In the last two, you have to introduce a t. You have to integral is 0 to infinity sine x upon x into x squared plus 1. What you need to do is sine of tx upon x into x squared plus 1 and then do the Laplace, correct. You introduce a t in there, yeah, and then after that put t equal to 1 after finding the answer. All right. Okay. So, now let us go to another interesting computation. We have calculated the Laplace transform of t to the power a, cosine of ax, sine of ax, e to the power t, right, t to the power k, e to the power at, t to the power k, e to the power at, sine bt. I can combine the sine and the cosine, they are after all complex exponentials. But then what is the Laplace transform of log x, log t? What is the Laplace transform of log t? Is log t of exponential type? Log t is of exponential type. So, what is its Laplace transform? Let us look at it. The Laplace transform of log t. Laplace of log t is integral 0 to infinity e to the power minus st log t dt. Now, do not have to write this, I mean it will be there in your Moodle, you can just listen, just watch. So, put st equal to u, what do you get? You get e to the power minus u log of u by s du by s. What is this integral? This 1 over s comes out 0 to infinity e to the power minus u log minus log s. So, the first piece does not the integral does not involve any s at all, It's a straight away an integral involved, which is a constant. The first, this integral here is a constant. So, the Laplace of log t is constant over s minus log s upon s. So, it is a constant upon constant minus log s upon s. What is the constant? The constant is integral 0 to infinity e to the power minus u log u du. What is this? First of all, how do you know that this improper integral converges? That is the first question. You have to show that the improper integral converges. The next problem will be to identify this constant. Is it possible to calculate this integral? What is the value of this integral? Do you recognize this integral? It is the gamma function. Well, a little more than that, it is related to the gamma function, but what is the relationship? What is gamma of A? Yeah? What is gamma of A? Integral 0 to infinity e to the power minus t to the power a minus 1 dt. Now, what do you have here? E to the power minus t log t. So, how can you get this from the gamma function? You can get it from the gamma function, true. Is substitution the only thing you can do? You can do something else also, no? You should do some of those exercises on gamma function, then you will get experience with these things. Suppose I differentiate the gamma function, what do you get? What is gamma prime of A? Gamma of A is what? Integral e to the power minus t to the power a minus 1 dt. So, what is gamma prime of A? What is gamma prime of A? Integral 0 to infinity e to the power minus t to the power a minus 1 log t dt. Now, what is the next step? Let me repeat. Gamma prime of A equals, please listen carefully, do not speak. Gamma prime of A equals integral 0 to infinity e to the power minus t to the power a minus 1 log t. Now, what do I do next? Put a equal to 1 and you get gamma prime of 1 equal to integral 0 to infinity e to the power minus t log t dt. Correct? So, the constant here, the constant C here is what? Gamma prime of 1. Now, what is gamma prime of 1 from our previous chapter? Minus small gamma, wonderful. Minus small gamma, absolutely. Okay. All right, some more amusement for you. Here are some more examples. Compute the Fulani integral. The Fulani integral is here, integral 0 to infinity e to the power minus at minus e to the power minus bt by t dt. Identify the constant in terms of the gamma function. We have just finished this problem. The second one we have just discussed. The constant is nothing but minus little gamma. What is little gamma? The Euler's constant. It is the limit of log n minus sigma j from 1 to n 1 over j. This object is minus gamma. This is minus little gamma, correct? And little gamma is also called the Euler-Mascheroni constant, correct? It was computed to 707 places and Gauss found a mistake in the 40th place. I told you this last time. And it is not known whether it is rational or irrational. as of today. Correct? No. The next problem is to evaluate the integral minus infinity to infinity exponential of minus bracket at plus bt by t dt by root t, and from that to compute the Laplace transform of 1 over root t x of minus b over t. This integral is really amusing. I mean, you should do this. It's a lot of fun. It's a nice, we can go on a nice merry-go-round when you try to calculate this integral. First simplification is that do it for a equal to b. Assume that the constants a and b are the same. Assume it's c squared or something like that. I can always do that. No, I can always replace t by, I can always scale that, make a scaling change of variables. No, put t equal to lambda u. Put t equal to lambda u and choose the lambda such that the two constants become equal. So I can, you must first do the problem with a equal to b equal to c squared. That is, we can reduce it to that case later. Then of course you will be completing the square and all those kinds of things. It's really amusing. You must do the third exercise. Recommended exercise. Recommended exercise. All right, let's go further. Shall we? Okay. Yeah. And there are some more integrals here. Prove that the Laplace transform of x to the power t 0 to infinity t to the power x minus 1 dx upon gamma x is 1 over log x, log s. So 1 over log s is a Laplace transform of something. So remember, it's important to have this list of examples. You might wonder what's the use of all these things. That's a question that you will say, okay, who cares that the Laplace transform of this happens to be 1 over log s? And why should you bother that the Laplace inverse of 1 over s to the power k log s is k to infinity t to the power x minus 1 upon gamma x dx? Yes? Who cares? Why should you bother about this exercise? You might say that after all, this function is not easy to calculate. Integral of t to the power x minus 1 dx upon gamma x. It's a complicated function, right? It's a complicated function, and its Laplace transform is 1 over log s. Now look at our list of Laplace transforms. Yesterday I made a comment that the Laplace transform goes to 0 as s goes to infinity, correct? I'll give you the previous slide later. I'm going to make an important comment and I want you to listen. So Laplace transform of 1 was 1 over s. Laplace transform of cosine was s over s squared plus 1. Laplace transform of sine was 1 over s squared plus 1, etc. So you have examples where the Laplace transform decays to 0 like 1 over s squared, etc. Laplace transform of 1 over root t is root pi by root s. So there is an example of a function whose Laplace transform decays like 1 over log s. We have seen that there is no function whose Laplace transform decays like e to the power minus s. If you want an e to the power minus s kind of decay, it doesn't exist. The function doesn't exist. Whereas if you can ask for a 1 over log s, 1 over log s also goes to 0. There is a function whose Laplace transform is 1 over log s. And then for the log t, it is c minus log s upon s. That goes to infinity slower than 1 over s, but much faster than 1 over log s. So there are there's a nice hierarchy of functions whose Laplace transforms go to 0 at a variety of rates, correct? All right. So is it clear? So if for that reason, if for no other reason, these examples are interesting. if not important. You know, you must have a stock of examples. Only then you can look for some kind of a theorem. You would like to ask for a theorem given a function f of s. What are the conditions on f so that it will be the Laplace transform of something? Sufficient conditions are known. According to Deutsch, necessary and sufficient condition is not known. Whereas the situation is much nicer for the Fourier transforms. The Paley-Wiener theorems give you a very complete answer. The story is not so simple for Laplace transforms. So here is the previous slide again for those of you who want to write down the remaining exercises. So now I hope I am able to convince you that the chapter on Laplace transforms is not some routine algebraic matter of computing partial fractions. Take a differential equation, apply Laplace transform, get a rational function, take the partial fractions decomposition and so on. Things are not so simple, things are little more complicated, things are deep in fact. So these are Fourier transforms again. By the way, there is a comment here. We have computed the integral 0 to infinity of cos x psi upon x squared plus a squared dx. If you try calculating the integral of this, you are going to run into some serious difficulties. It is not so simple. What is the, try calculating this integral. I will be very interested if you succeed. It will be very interesting to calculate this in closed form. You may be able to calculate the Laplace transform. You can call, instead of psi you put t, and you can do the same trick again, take the Laplace transform inside the integral and you will get the answer. But remember, we have to find the original function. That is not a joke. Recovering the original function from the Laplace transform is no joke. We have done it only for rational functions and its close cousins, which are obtainable by obvious shifting theorems. Right? All right. Further examples. Now let us go to. Now we have computed Laplace inverse of a rational function. For which kind of rational functions? For rational functions of the form p of s upon q of s, where p and q are polynomials. What is the condition? Degree of p is less than the degree of q. Now we can work in the complex domain and we can write down the partial fractions decomposition, right? How does the partial fractions decomposition look like? You have ps upon qs. Over the complex numbers, you are going to write down the partial fractions decomposition. So suppose if you take a root of the denominator, say alpha, you are going to be looking at constant upon s minus alpha plus another constant upon s minus alpha squared, a third constant upon s minus alpha cube, etc. Right? So you are going to look at finitely many terms of the form, a linear combinations of terms of the form 1 over s minus alpha, correct, for varying, where the alpha varies over the set of roots. Is that correct? But look at this 1 over s minus alpha, 1 over s minus alpha whole squared, etc. 1 over s minus alpha can be written as the following. Pull the s out. I can write it as 1 over s times 1 over 1 minus alpha by s. Correct? 1 over s minus alpha is what? 1 over s times 1 over 1 minus alpha by s. 1 over 1 minus alpha by s, can you write it as a geometric series? You can, right? So you get a 1 over s times alpha by 1 plus alpha by s plus alpha squared by s squared plus alpha cube by s cube. But remember that there is a 1 over s factor. correct? So the series starts with a 1 over s term, a 1 over s squared term, a 1 over s cubed term, remember. It doesn't start with a constant. It cannot start with a constant. The Laplace transform must decay to 0, remember. The Laplace transform must go to 0. So it can't start with a constant. It's 1 over s into constant plus constant upon s plus constant upon s squared plus constant upon s cube, right. The same thing is true for 1 over s minus a the whole squared. Pull the s out, you will get 1 over s squared. 1 over s squared into 1 minus alpha by s to the power minus 2. Apply the binomial theorem for negative exponent. You are going to get an infinite series, correct. How does this infinite series look like? Constant upon s squared plus constant upon s cube plus constant upon s to the power 4 and so on. So this is true of every term now. So after you take the rational function p by q, write down the partial fractions expansion, you play this game. The whole expression can be written as constant upon s plus another constant upon s squared plus another constant upon s cube and so on, correct. Now rational functions are not the only functions for which this can be done. There is a variety of examples where I can do this. So whenever the function capital Fs can be written as a series constant upon s plus constant upon s squared plus another constant upon s cube, etc., I can always calculate the original function of which this is the Laplace transform. Only problem is that the original function will not be computable in closed form. You will get the original function as an infinite series. That is the next project. Further, though please do not write any of these things, it is too much to write. Just watch and let us work out the example. Concentrate on the example, the theory will go through. Why should the Laplace transform go to 0 as s tends to infinity? That is the statement of the Riemann-Lebesgue lemma. The Riemann-Lebesgue lemma says that the function f is of exponential type, then the Laplace transform will go to 0. Remember that we are working with functions, and not only functions, functions of exponential type. If you work with distributions, then the story is entirely different. The Laplace transform of the Dirac delta is 1. The Laplace transform of the Dirac delta is 1, but the Dirac delta is not a function, it is a distribution, and we are not discussing distributions in this course, nor can you do it in your universities. It's distributions are too complicated to be discussed at the bachelor's level course. Let us stick to functions, and for functions of exponential type, the Riemann-Lebesgue lemma tells you that the Laplace transform goes to 0. Now let us look at further examples on the computation of the inverse Laplace transform. Suppose that the function fs has a series expansion of the form f of s equal to sigma n from 0 to infinity a n upon s to the power n plus 1. Look at the n plus 1 here. The series begins with a 1 by s terms. It does not begin with a constant term. That is the point. Converging, the series must converge for mod s bigger than r. The series must converge for mod s bigger than r. Then the original function can be recovered by taking term by term Laplace transform. That is, you apply the Laplace inverse operator inside the summation sign. And what is the Laplace inverse of a n upon s to the power n plus 1? A n comes out and gamma n plus 1, this n factorial is gamma n plus 1, remember. So the Laplace transform of this is this. So the inverse Laplace of this is this. So I can proceed to computing to the computation of the inverse Laplace transform term by term. What comes out? The original function presents itself in the form of a power series. You have obtained the original function in the form of a power series. Before we proceed to the proof of the theorem, it will be instructive to look at a concrete example, and the example that I am going to select is to compute the inverse Laplace transform of 1 over square root of a squared plus s squared. These two things are going to be left as an exercise for you. This first one we are going to do, the second and the third one are exercises. So, jot down just these two things, just these two, the last two. Compute L inverse of 1 over s e to the power minus b by s and L inverse of e to the power minus b by s upon root s. This last example is very important. This last example is very important. And first one we shall take up over here to illustrate, all right. Okay. Let us go to the first one. Okay. The first example, assume without loss of generality that a is a positive real number. Assume without loss of generality that a is a positive real number and s is bigger than a. Then 1 over square root of s squared plus a squared. What have I done here? This is written as, I have pulled out the 1 over s as usual and I get 1 plus a by s the whole square to the power half. Then what is the next step? Apply the binomial theorem for, oh good heavens, I have made a mistake. There should be a minus sign here. There should be a minus sign here, and there should be a minus sign here, a minus sign here, and a minus sign here. Anyway, let us put in the minus signs as we go along, does not matter. So, is it clear that the function in question is 1 over s into 1 plus a by s the whole square to the power minus half. Am I right? Am I right that I made a mistake in the exponent? All right. Then what does the binomial theorem say? 1 plus x to the power alpha is 1 plus alpha x plus alpha into alpha minus 1 upon 2 factorial x squared plus etc. So, your alpha is minus half, correct. So, have I got the binomial theorem correct? Alpha into alpha minus 1 into etc. alpha minus j minus 1 upon j factorial, all right, into a by s to the power 2j. This is a binomial theorem expansion. Now, what do? We go proceed to taking the inverse Laplace transform term by term, right. So, this minus sign will again come all the way over here and we will get this, correct. So, is this step clear? Take L inverse term by term, and then what do you get? You get from this 1 over s to the power 2j, I get a 2j factorial here. And what have I done with this whole thing? What I am going to get j powers of 2 from these things, right? And I am already having a, so that is going to give me a 2 to the power j, correct. And what is going to be in the top? 1 into 3 into 5 into odd numbers. What is missing? 2 into 4 into 6, that is missing, right. What is 2 into 4 into 6 into etc. 2j? 2 to the power j into j factorial, correct. So, I introduce the 2 to the power j factorial upstairs and downstairs, and I will get, and the 2j factorial will cancel out, and I will get a j factorial squared into 2 to the power 2j, but this minus 1 to the power j, yeah, in the last step I somehow written it correctly, I do not know how. Maybe I did the work, maybe I did the calculation in rough and I transcribed it. So, this is a transcription error, right. So, there is a sigma j from 0 to infinity, you have a j factorial squared. Where is the j factorial squared coming from? One from here and one from the, trying to make the product in the numerator into a factorial, 1 into 3 into 5 into 7 etc. I introduce numerator and denominator 2 into 4 into 6 into 8 etc. So, the numerator simply becomes 2j factorial, the denominator becomes 2 to the power j factorial. So, one more 2 to the power j has come, and so that becomes a 2 to the power 2j and a j factorial squared, and there is a minus 1 to the power j, correct. So, this is the Bessel's function of order 0. This power series is called the Bessel's function J0. So, the Laplace transform of J0 of AT is 1 over root of A squared plus S squared, correct. So, we obtained something which is not a rational function. We obtained the inverse Laplace transform of something which is not a rational function. This is not a rational function.